for your introduction. And thank Mauro for inviting me here. And thanks, the KITP, for hosting us here for this, for organizing this really nice program and the roundtable discussions. As you can see, actually today, I'm going to show you, some, functional materials for different energy applications. And so I'm Zheng from Northeastern University in Boston, and a couple of years ago, actually, my group, also studied a lot, in theoretical physics, and we applied fluctuation of electrodynamics, okay, to calculate Casimir force, Casimir van der Waals force, and modify the Lifshitz and the van der Waals force between two plates and spherical shapes. And also we applied the fluctuation of electrodynamics, okay, to evaluate, to determine the Poynting vectors, just E cross H, for the near field thermal radiation, and for different shapes, and also between plates, between spherical shapes, like sphere, single sphere, shell, and this hollow sphere, just like cavity in medium. But a couple of years ago, and we kind of transited our research interest, from theoretical research to more applied, physics research. So that's what I'm going to show you today. So most of the project I'm going to show today actually is related to materials. Okay, as you can see, okay, I'm going to show you the multifunctional materials. Multifunctional, actually, these days, actually, when we study materials, okay, particularly energy materials, okay, we're more interested in, okay, the functionality, the multifunctionalities. We hope actually one material or this material actually we design actually can own, multiple multifunctionality, okay, at the same time. Here, actually, we might be we're more interested in the light absorbing material, water absorbing material, and the self-cleaning, super hydrophobic surface, and the high temperature stability, okay, of the materials. And also the material here, I didn't use nano micro material, and also I didn't use metamaterial or metal surface here. I simply put the materials here because I just want to show you, so we can simply, just broaden our ideas, when we search for different materials. Okay, so we studied, my group studied actually the nanomaterials, okay, in the past almost 10 years. And still, these days we also work on, okay, the metal surface, okay, the metal material design for thermal emitters, for thermal absorbers, for different light absorbing materials. Okay, we use the e-beam lithography and the photolithography, and we use different type of micro clean room technologies, okay, for different nanomaterials. And I don't want to bore you today, so today I just want to bring, okay, some fancy, okay, or materials, okay, that's made of cost-effective materials, low-cost materials. I'm going to show you how we use the low-cost materials, okay, to achieve, okay, on the same goal. Okay, the material actually could achieve, okay, maybe the even higher or maybe the similar light-absorbing materials, unlike metal materials, metal surfaces. And for energy applications, and I'm going to show you, okay, a few energy applications, like the solar power, solar-driven water desalination, like the passive radiative cooling, and also like the TPV, okay, near field TPV energy harvesting as well. Unlike the previous talk, like Jeremy gave a talk actually about the measurement of Casimir force, and unlike the Bongji's talk about the measurement of near field radiation, today I'm going to show you, okay, more the applications, okay, totally different applications. And I came here actually 3 weeks ago already, so I already gave 2 talks, just 2 weeks ago. So if any of you is interested actually about my talks, actually seek the information. So all of our talks have been made public and online. So the first talk I gave about 2 weeks ago actually is about actually fundamentals and the applications of the about dynamic control of radiative thermal transport, and the second one about multifunctional materials. So in this presentation today, actually you might see some of you actually, if you already attended actually my second talk, you might see okay a few slides, maybe 3-4 slides, with overlapping contents. Okay, so here's the outline, okay, of this talk today. And as you can see, actually from all of these bullet points, I tried my best, okay, to summarize, okay, so the recent work that we have done, okay, in my group, okay. So I didn't, okay, I'm going to show you, I won't show you the old work. I'm going to show you, okay, the work we have done during the past 3 years, okay, publishing, dating from 2019, okay, today. And also I tried my best, okay, to summarize, okay, most of our work in one slide, or even in one slide, okay, you can see maybe more than one project, okay. I just want to give you an idea. So what I've done, and also want to provide you with some insights or ideas from material science, okay. So Let's see the first one about a passive radiative cooling. Okay, people have studied passive cooling during the past decade or even longer time. And passive cooling is one of the hot topics, and some of you already heard like this one. And today I just want to show you two works we have done, in the past 2 years, from the materials point of view. People study the different materials, the nanomaterials or some really fancy porous materials to achieve the passive cooling performance. And for some of you, if you are not familiar with the passive cooling technology, I'm going to show you actually what is that. I think the next slide actually I have this slide here. For passive radiative cooling, people would like to achieve the cooling performance without the use of electricity, or try to reduce the use of electricity. We simply rely on maybe the material itself. So how does it work? Let's say you have a thin film material, or you design a material. This material has two goals. The goal number one is going to reflect as much energy as it can. So sometimes, like you have already read some article these days. Dr. Shuling Ran's group at the Purdue University, they already invented the whitest paint. The whitest paint can reflect more than 99.9% of the solar energy. This is the goal number one. Try to reflect most of the sunlight. And goal number two, such a surface could actually re-emit energy. And then at the particular infrared wavelengths. Normally, when we talk about actually this, the infrared wavelengths, we talk about actually the first transmission window of the Earth. That is between 7.8 microns and 13 microns. If any surface could re-emit energy between 7.8 and 13 microns, this energy can simply just go through the Earth's atmosphere, and then it gets lost to the ambient. And this is only the first window, and also we have several other windows, beyond, maybe between 20 and 22, and also for even longer wavelengths. But most research will simply focus on the first window of the Earth transmission, between 8 and 13. So if such a material, could own a really high reflectivity for visible light, for solar energy between 0.4, 0.5 to maybe 1.1 microns, and as well, such a surface can also emit energy, with really high emissivity between 7.8 and 13 microns. So this material is perfect for passive radiative cooling. That's the idea of the passive radiative cooling. So let's go back to this slide here. So my group, studied the fiber-based, thin film materials, or sometimes we call it cooling papers. It's a paper we published, last year, at ACS AMI, and we've used recycled papers. Unlike, some nanomaterial or micromaterials, our goal is to reduce the cost. For these practical applications. The other day, when we went to, when I went to, the department suite during the pandemic, so I just saw actually. Normally we won't see that actually. No, but I just saw actually, this recycled bin, full of recycled papers, and then I just, just asked myself, so can I do something, with the recycled papers? Maybe you can do more. I know actually there are other applications related to the use of recycled papers. So actually, I just brought some recycled papers back to the lab, and what do we did? We simply use a high-speed blender to blend them to make a paper pulp. To put the recycled papers, the paper form into the fiber form, and now we're going to study how this fiber is going to actually improve the efficiency, the passive cooling performance. So next, I'm going to show you. I'm going to use 4 or 5 slides to show you the passive cooling enhancement, using the recycled papers, the cellulose fibers. And after this work was published last year, and also we continue actually this work. But today I want to show you, this work. This work we just published, this year, in Nano Energy in February this year. So this cooling paper was made of recycled papers. And then, we received, quite a few interest, from industry. People are just asking me, whether or not we can commercialize this idea, or is that actually definitely we can do that. And we received a lot of, questions, from the people actually, from end users. And one comment that we received, last year, is about for outdoor applications. This material already owns a really nice optical properties, just like the one I just showed you. It has a high reflectivity in solar wavelength range, and also has high emissivity, in the first transmission window of the Earth. But for practical applications, for outdoor applications, okay, the durability is the most important, and the fire retardant, fire resistance. Can we simply apply paper to your house as a roofing material? No, definitely no. So that's why we studied a different type of fibers. So we invented inorganic fibers. So we used hydroxyapatite. Hydroxyapatite is one type of calcium phosphate, phosphate material, and we looked this material. This material, definitely has a really high fire resistance. For the spark form, and also we find actually, you can buy hydroxyapatite, in its powder form, but its fiber form is not available at all. So we thought actually maybe we're able to use this material and fabricate hydroxyapatite fibers, and then if we're able to fabricate hydroxyapatite fibers, we can simply use this fiber to make paper made of these inorganic fibers. So we call this one meta paper, and then actually we succeeded. And such a material also owns a really high reflectivity, around 0.94, and also has a really high high emissivity, up to 0.92. And also this material is super hydrophobic as well, like this paper, like the organic paper. Organic fiber-based papers, and one particular, this material is fire retardant. So if we just burn this material, and this material actually cannot actually get burned easily, and this material can be really good actually for the outdoor applications. But next, I'm going to show you a few slides, regarding the first project. Now down the second one. So I already gave you the story about actually recycled papers, why we are interested in the recycled papers. Now let's see. The paper actually really simple. Just the paper actually we use daily. We simply recycled the office paper and print papers. And as you can see, the recycled papers or cellulose fibers themselves are hydrophilic, not super hydrophobic. So for outdoor applications, we were looking for a material with a hydrophobic surface, or even better, with super hydrophobic surface. So this is what we did. For this one. And in this spectrum here, I just want to show you the mechanism of the passive rate of cooling. So for the visible light range, such material should own a really high solar reflectivity. And for the first window of transmission window of the Earth, between 10.8 and 13 microns, such material should have really high emissivity. And this is a spectrum actually, the measurement data actually about the cellulose fibers. And also to achieve the passive cooling, the material, just like I said, actually should own a really high reflectivity between this range, 0.3 and 2.5 microns, and the high infrared emissivity between 8 and 13 microns. And hopefully this material can have a close to unity, an angle independent thermal emission. So in these two figures here, I just showed you. So we plot the reflectivity for the visible, for the solar energy between 0.3 and 2.5. You can see that it independent of angle, and also for the emissivity. For this reference of interest here, like this blue curve it shows here. It also shows a really high. It maintains a really high emissivity. And independent of angle. This perfect material. But then actually I asked, so what's the reason? So what's the reason? To cause such nice, optical properties, from the recycled papers. So we look into this material, and we found out, we demonstrated experimentally, simply because of the COC bond, this carbon oxygen bond inside the cellulose fibers. So this material could have a really high the high solar reflectivity and the high emissivity. So you can see that actually for the reflectance, between 0.3 and 2.5 microns, it's not that high. It's only up to 0.89. It's not perfect at all. So during the past few years, a lot of groups already published the papers in this field, in the field of passive rate cooling. They all report actually the solar reflectance that can easily be achieved, up to 0.99, 0.96, or even larger. But I just want to argue with you. So this material is low cost material. We can simply use the recycled paper to achieve this really high reflectance, even though it's not up to 0.99. Even 0.89 is not bad at all, considering the cost here. Next, for other applications, as I mentioned to you, cellulose fibers are hydrophilic. So we have to transform this material into hydrophobic. So we simply use the Teflon PTFE particles, and we cover the cellulose fibers by PTFE particles, and really simple. Really simple step. We can easily turn hydrophilic surface into super hydrophobic. We measure the contact angle of the PTFE coated actually the cellulose fibers. The contact angle is over 165 degrees. So it's really perfect super hydrophobic. So this is a really nice thing. And also the question is, so which such a coating, PTFE coating, is gonna reduce the performance or even enhance the performance. So we simply measure the reflectance, solar reflectance, for the PTFE coated cellulose fibers, surprisingly good. It's improved the solar reflectance from 0.89 up to 0.96. Really simple coating. So you see, we simply use the recycled papers with the PTFE coating. Both of materials are non-novel at all, and also they're all cost-effective. We can achieve high reflectance up to 0.96, and also infrared emissivity still maintains really high. It's something I want to show you. And also we run the 4 season, the 1-year outdoor test in Boston, and we're able to achieve the passive cooling, the sub-ambient cooling by 6 degrees Celsius, the 10 Fahrenheit. And the power around over 100 watt per meter square. So here's the setup of our system. We set up at the rooftop of our engineering building on campus. So I might skip some of the slides, because of the time limit here. And the next question is, so how do we really apply this material, and how to attract more customers? As some of you might have been aware, the people already study the different type of cooling papers, the cooling products like the white paint, there's a white polymers, and a different type of polymer-based materials. But all of these materials are white, because the white material has a really high solar reflectance. That's the goal. And the question is, as an engineer, I ask myself, so whether or not actually we can change color of the material and still we can maintain or can achieve the similar performance or even better, because most of the end users, we interviewed, they may not be in favor of white products for their building, for their trucks, for their cars, for their outdoor facilities, like a tent. So we simply studied, the different color, and we might compromise, some optical properties, in the visible light range, but actually what we achieved. So we simply dye, the cellulose fibers, the blue dye, red dye, green dye, we try different colors as much as we can. And as you can see here, the performance is not bad. It's not that bad, The black bar here shows you, the solar reflectance and also the infrared emissivity for, the white cellulose fibers, red dye and green dye. You can see the performance is not bad. For the solar reflectance, for the red dye, it's just simply reduced from 0.9 down to maybe 0.89 also. For green one, also, slightly reduced. You can see here, the minimum value here is 0.8, and the minimum value is 0.8. So it's not bad, and sometimes it even get enhanced. So it's going to actually broaden applications. So for passive cooling, for applications, people may not simply focus on the white products. They can simply focus on maybe they can choose it. Whatever color they want. If you want to have a really nice fancy the red roofing, it's up to you. You don't have to really stick with the white color for your cooling products. We demonstrate experimentally, red dye, green dye. You can see for the solar reflectance between 0.3 and 2.5, and for the infrared emissivity between 7.8 and 13. Not bad. Not bad. Next question. Next question. We already achieved this. We apply our cellulose fiber-based products to the existing roofing materials. Because our goal is to apply this material. As an engineer, and we apply the cellulose fibers over existing roofing materials like the concrete, the basswood, tin, metallic material tin, and we demonstrate the performance already experimentally, and also we already improved the surface feature from hydrophilic to super hydrophobic, and also we changed the different colors. And the next question is how do we further reduce the cost? Because in this talk I want to show you our goal is to create low-cost, cost-effective materials. And this material, cellulose fibers are made of recycled papers already has a low cost, as we all know that. For a real large, maybe 1 meter by 1 meter size paper, the cost only less than 20%. I'm sorry, 20 cents. Only 20 cents. But how do we reduce further the cost? So this forced me to study the recyclability. To achieve the goal of sustainability. So if this material can be recycled further, maybe we can simply reduce further this cost. That's what we do. This is what we did here. And here there's a video clip that showed you the super hydrophobic surface and all. How this look like. So we simply made recycled paper ourselves here. Okay, so in this figure A here, this is the cooling paper or cellulose fiber-based papers, okay, made of recycled papers. Okay, and figure B here, paper pulp. We simply use the high-speed blender to make a paper pulp. And figure C here is the recycled cooling paper. Okay, so after maybe one day exposure to the sunlight, we just brought it back to the lab. We use a high-speed blender to remake the paper pulp and make the recycled paper. And how does it look like? And then we simply measure the spectra. Okay, you can see the blue curve here shows you the pristine just original cooling paper made of recycled papers. And the red curve here just shows you the recycled actually the cooling papers we made. It's almost the same. Okay, if you compare this solar reflectance and the infrared emittance, it's not bad. After as a mechanical engineer, our goal is to improve the properties. Okay, so we already achieved really nice optical properties. Okay, next step we want to achieve the mechanical properties. Okay, like the strain, we measure the stretch strain curve, and like this red curve shows you here, this can be comparable even to the artificial wood. And also we run the surface vibration test with just plate actually weight on 100 gram weight on top of the cooling paper, and we just spread it along 10 centimeters, and then rotate the paper not different angle, and rotate it and then slide it on the sandpaper, silicon carbide sandpaper with a 400 grade. For another 10 centimeters. We just repeat this process over 100 times, and then we just brought this material back to the spectrometer. We have to measure the solar reflectance and infrared emittance. This material still can maintain a really high optical properties. Okay, so next project, about the Solardriven model designation. People have also studied this one for past few years. And also 2 weeks ago, in the Gang Chen's presentation, he also mentioned that people already study the hydrogel-based material from Guihua Yu's group. So they study hydrogel based the solar evaporator, and also experimentally we demonstrated. People demonstrated the water evaporation rate can go over the limit. The limit actually, the natural limit is 1.4 water per meter square per Kelvin. And our goal is to keep increasing this evaporation rate and the higher the better, and with the low cost materials. But here I just want to give you a general idea about the interfacial evaporator. People study the interfacial evaporator, made of the hydrogels, the porous materials, and some other the carbonized the carbon foams. And also people study the different geometries in 2D form and also in 3D form. 2D form just like you have a thin film evaporator, or you have a multi-layer structure, but actually all of these materials are floating at the water interface. Just we treat this material, all these structures as a 2D. 3D structures, people also studied like a smart tree. So actually we designed a tree-like structure. They have a root inserted into the water, and water will be absorbed through the root and through the trunk, and then actually to reach the leaves. And also people also study different the 3-dimensional structures. And our work published last year at AFM. So we studied the 2.5D structures. What is a 2.5D? Actually, we just defined this 2.5D because we simply use the 2D structure. So as you can see here, so our evaporator, interfacial evaporator is still a thin film porous structure. It's a 2D structure. But we simply just leave this material with an angle, with a tilt angle, and insert actually one end of this porous material into the water. So it's make a 3D application. But it's not a 3D structure, so we simply name this one 2.5D. And you can see the benefit here. We have actually more surface here, and also only have a really, really small area in contact with the water here. So water can be easily transported from this, the bottom of the porous structure to the top. The material we use here is copper foam. And as you know, the copper foam is hydrophobic or even super hydrophobic. It is not good for water transportation at all. So the first step, we need to treat the surface. We need to transform this hydrophobic copper foam into hydrophilic. And we simply grow the nanostructures, the copper oxide, the CuO and the Cu2O onto the copper foam. And then this material totally okay, hydrophilic. It can easily actually transport water from the bottom, okay, to reach to the top, okay, of the copper form. And this material has a really nice water absorbing property and evaporation property. And the next project we have done last year is, okay, like I repeated multiple times, our goal is to reduce the cost of the functional materials. So we are also abandoned the use of this the copper form, the metallic materials. We switched to the farm waste materials. Also during the pandemic, actually we drove to the local farm, try to get some dairy on the local farm. While waiting for the dairy, actually I simply just talked to the owner of the farm. Because I saw so many cows and horses run or resting on the farm, I said, can I get some cow manure, cow dung? Because all of the cow manure, cow dung, they're extremely low cost materials, right? Cow manure, and people already try to use recycle the cow manure, for fertilization, for farming. And then I asked myself, maybe we can use the cow manure, to do something else, and transform this material into more functional energy material, And the cow manure, what is the main constituent? The main constituent of the cow manure is just cellulose fibers, just carbon, natural carbon. We don't have to use carbon nanoparticle, carbon nanofibers at all. We simply use the natural carbon waste material. So we brought actually a bucket of the cow manure, and we carbonize it up to 600 degrees Celsius. So it's going to kill all the bacteria in the cow manure, and then we simply use some mechanical molding to make the cow manure, carbonize the cow manure based material. This material itself is carbon-based porous structure, like a carbon foam, but with extremely low cost. And we test this water absorbing the property of the cow manure, and it shows a really good property. This is the dried manure. This is the carbonized manure. After 600 degrees C treatment, and also we're able to achieve the water evaporation rate, up to 5.3. 5.3 kilograms per meter square per Kelvin. That means for a unit time for 1 hour, for a unit area 1 meter square, we could actually collect up to 5.3 liters of water. And also we tested the water quality of the collected water actually through this technology. Sodium concentration is really low. It's less than 5 milligram per liter. It definitely meets the water requirement, the drinking water requirement set by EPA and the WHO. So this one is also defensive work. Other two work we worked in the last year. I also focused on the different waste materials. Previous one actually we transformed the farm waste material, cow manure or horse manure, and then we simply switch our interest into some ocean biomass materials. And as you can see here, I'm going to spend actually 4 slides later to show you this project. As actually we are from Boston. So we have access to seafood a lot. Like lobsters, and clams, and shells. So this time actually I simply asked my student, maybe we can do something with the ocean biomass materials. Because our goal is to desalinate ocean water and transform it into the drinking water, maybe it's better to make an ocean-to-ocean cycle. We can use the ocean-based material, waste material, and then transform into the functional material to desalinate the ocean water, and we succeeded as well. This time actually we focus on we fabricated the hydrogel materials. We simply use the 2 ocean biomass material. One is Ketosan. Ketosan is a powder form of the pearl, the pearl, or clams or clam shells, lobster shells. So we use Ketosan as the skeleton of the hydrogel material, and also we use the cuttlefish ink. Cuttlefish ink is squid ink. It's black. It's a natural black liquid. We know that. We simply purchase the food level squid ink, cuttlefish ink, and in our lab we dry that, and also we use a ball miller to make the natural carbon nanoparticle ourselves, and we are able to obtain the carbon nanoparticles, with average size of 20 nanometers out of cuttlefish ink, and we use the cuttlefish ink and mix into the Ketosan as a skeleton. We make hydrogel-like material. I'm going to show the result later in the next 4 slides. And we also will achieve a kind of high water evaporation rate, up to 4.6. So 4.6 liters per meter square per Kelvin with the use of these low-cost ocean waste materials. Next, okay, so we studied the farm waste, ocean waste, and next actually forest waste materials. Okay. Forest waste materials still about 2 years ago, I went hiking actually myself, okay, in the local state park. That's the Middlesex Fells, okay, to the north of Boston. In the fall, so while hiking, you saw actually the tree leaves all everywhere. Okay, particularly maple tree leaves and oak tree leaves. So I asked myself, maybe I can do something else with the tree leaves. Okay, just like what we did to the cow manure. Okay, so the other day I just brought actually the trash bags to the state park, and I collected the tree leaves. Oak tree leaves in one bag, and maple tree leaves, the yellow one and the red one in the different trash bags. And I brought them to the lab. Actually, my student and I were just there's a scissors to separate the stem and the leaves, and then we carbonize this material, and we just repeated what we did to the cow manure, and we also study the solar rejection property and the water absorbing and the light absorbing property of this material. It also turns good. This material does not actually yield very high water evaporation rate, but it is good to study the tree leaves material. And next few slides I'm going to show you, so this solar-driven water desalination project. The people study the water desalination technology a lot. In the past few decades, people use totally different techniques. Use the osmosis technique or use the heating techniques. And for the heating techniques, people also use 3 different types of heating. Bottom heating, if you set up a metallic heater at the bottom of your beaker or tank, you can boil the water, right, to evaporate the water, but with really low efficiency, as we know that. Or bulk heating, to heat actually entire the water in the tank, in the container, or interfacial heating, it turned out to be this one with a higher water evaporation rate and a higher efficiency. So we just studied interfacial heating, and also like I introduced to you, people study the 2D and the 3D structures. And in our group, we focus on the low-cost material, the 2-dimensional structures. And for such a material, this material on top, at the top surface, this material should be has really high light absorptivity. Usually it's black material like a black body has a high solar absorptivity, and the normal way or the easy way to treat this material to get it into black is to carbonize it. If you're able to carbonize the material, turn it into black, you can improve its solar absorptivity, and also this material normally for most cases must be porous material. Porous material can absorb water easily due to the capillary force, and or like hydrogels, also porous material can absorb water easily, through the hydrogel. From the bottom, to reach to the top, to the light absorbing layer at top. And also usually, people study or place a thermal insulation layer at the bottom, try to reduce, the heat downwards, from the heated top area, to the bulk water. And this is our work, and I just skip this slide, just shows the application, the application of the hydrogel using the cuttlefish ink and the ketosome. And this is the result actually we have, and we tested actually the thermal conductivity of the wet and dried form of the hydrogel, and also we test the water absorbing the property of the material, and it can absorb water easily. Within 3 milliseconds, water can be easily absorbed. And also we tested the mechanical robustness of the flexibility of the material. And here shows you the desalination performance. It could, that's like I mentioned actually, it could generate 4.6 liters of fresh water per meter square per hour. And also we studied a different type of the water absorbing. So if you have your copper foam, if you have your PVC foam, if you have a foam actually with a direct contact to the water, so you might lose some of the heat, from the bottom surface, into the bulk water. Just the way we try to avoid it. That's why, we place a thermal insulation layer at the bottom, and also we are able to absorb water through the cotton wipe, from the water to reach to the top of the evaporator. And also we measure the temperature. You can see, with the water pass, the cotton wipe here, the top surface temperature actually maintains at 46 degrees Celsius is her temperature. And the next step actually we just demonstrated, is the solid rejection performance. People might question, so all of those fresh water already evaporated out. You have generated the fresh water, but where are those salts? The answer is that all of those salts actually it's gonna be block all of those micropores or microchannels. But eventually, maybe during the nighttime, all of the salt actually will be washed away and go downwards, into the bulk water. This may not be a good way, but imagine if we pump the water actually into a large tank or container, okay, is working during the daytime, and during the nighttime, actually, all of the salt actually will be washed back into the container. And maybe after a few days, okay, I mean, you have extremely high salinity water. Okay, so you might easily obtain, okay, the salt as your side product, okay, through this water desalination project. This is actually when we demonstrated, okay, within about 3 hours, okay, so all of this, okay, the salt actually can be easily, actually, okay, dissolved back into the water, the bulk water. And also we tested, okay, I mean, the water desalination rate, okay, for the different, the sodium concentration, okay, 2.5 rate concentration up to 10. It shows actually really nice, okay, the linear change of mass, and also maintain a really high solar reflective, the solar driven desalination rate. Next few slides, okay, I'm just go through really quick, okay, really quick. Okay, I showed you, some other multi-functionalities actually of interest. The first one, okay, is about a high temperature stability. Like, in the previous talk, the Lilia just mentioned that, okay, so he designed, okay, and the near field TPV system, okay, and also they're able to test, okay, the high energy conversion efficiency and the rate. And in this time, actually, we didn't actually set up our system to measure, okay, the energy conversion efficiency at all. Actually, our job is to demonstrate the high temperature, okay, stability of the material. If this material, if it's a thermal absorber or thermal emitter, you design fail at a high temperature, okay, I mean, there's no need to talk about actually the efficiency or energy performance at all for the CSP system or far field or near field TPV systems. So we published 2 papers in the past 2 years, and we designed, okay, the metamaterial, the metal insulator metamaterials, okay, just like what we showed here, the multi-layer materials. And this material is thermal absorber, and also we designed a thermal emitter as well. And we used our vacuum furnace and a muffle furnace, okay, and a tube oven in our lab. So we're able to heat up, the materials up to 1,600 degrees Celsius. And also we run, okay, experimental work, and our goal was to demonstrate the thermal insensitivity of the thermal emitter, thermal absorber materials for both far field and near field TPV energy conversion systems. And this is the work actually I want to show you. And the next slide, okay, just the one I just showed. So for passive cooling, okay, and people also question, okay, so whether or not actually you can control the passive cooling. For example, actually it's useful. It is demanded, okay, for summertime, but for winter time, okay, nobody needs that. Okay, you cannot simply replace your roofing for different seasons, okay, throughout the year. So if we are able to control, okay, the passive cooling, okay, using different mechanisms, you can either use the phase change material or you can use the mechanical deformation mechanism, okay, to stretch or compress, okay, your passive cooling material. Okay, this can be really good to achieve the on-off mode. So this is the work actually I showed in my second talk, and I mean 2 weeks ago. PDMS layer here, and also this material is made of PDMS, the soft material, stretchable material. So under mechanical deformation, you're able to stretch and compress this material. On the back side, you have a silver coating, and inside actually you have multiple species of nanoparticles, which could open a broadband window, okay, of interest. And our idea is actually you achieve actually on mode, okay, for the summertime, okay, is turn on mode for passive cooling. And in the winter time, okay, you just switch, okay, this layer, okay, you just shut down the passive cooling performance. This is what we did experimentally, and you can see that, okay. So if you, for zero strain, it keeps it on mode. And if you stretch, okay, the PDMS layer, okay, up to 128%, okay, up to its maximum stretching limit of the PDMS material, okay, is reduced its emissivity between this, okay, 8 and 13 microns. We can treat this one as off mode. And also if you focus on, okay, the visible light range, okay, does not change too much, okay, you simply change the infrared wavelengths, okay, of interest here. And this is the project, I mean, I just showed you. So we first time actually demonstrated, okay, so with the multiple species of nanoparticles, we are able to create it, okay, a narrow broadband thermal emission. I also showed this project before, let's say. So if I have a thin film material, okay, by inserting or doping specific species of nanoparticles, you might be able to observe narrowband peaks, okay, or multiple narrowband peaks. But our goal is to create a broadband peaks. How are we going to do that? Okay, so we simply, our goal, for example, if we want to study, we want to create a broadband window between 8 and 13 microns, for example, we just screen, okay, the different nanoparticles, different materials, and we just find, we targeted two types of materials. One, silicon nitride, the other one boron nitride. Each of them actually could create 2 narrowband peaks, okay, within this range, between 8 and 13. So I asked myself, okay, so can we demonstrate it, okay, if we simply mixed, okay, these 2 specific nanoparticles, okay, into a thin film, you're going to observe the 4 narrowband peaks, or it's going to create a broadband emission peak. Okay, we demonstrate experimentally. Okay, you can see, actually, okay, we create a broadband, okay, emission window. So let's just give your idea. So maybe in the future you want to design something. For example, to design a broadband thermal emitter absorber, actually, you can simply consider doping technology to create a broadband idea. And next one, the phase change material. This work, we published a few years ago, and also worked with Morrow's group, together. So we designed actually the thermal diode and the thermal transistors made of phase change material, VO2. Vanadium dioxide has a phase change temperature around 341 Kelvin. One temperature higher than this temperature, okay, it turns to metallic form. Temperature less than that is dielectric, okay, insulation form. So we simply use this material to design, okay, a non-contact mode, the radiation-based thermal diode to control the radiated heat flux from one, okay, to the other direction, okay. And our goal is to, I don't have to go that deep. I don't want to show you the result. So rectification ratio, okay, of the thermal emitter already reached up to 160, over 161, okay, last year. So with Morrow together. And if you have one thermal diode, and these are 2 terminals, with a passive active terminal and a passive terminal. Active terminal, okay, with the VO2, the material. So now actually, if you have 2 thermal emitters and place them back to back, so it creates a 3-terminal structure, right? So 1, 2, and 3. So this gives us an idea. So it's a transistor-like material. So maybe we are able to demonstrate a transistor-like phenomena. And in this work, we also designed actually a non-contact mode radiation-based thermal transistors. And this work actually, we published a few years ago in APL. Okay, so that's our first work, and this one serves as a fundamentals, okay, to our other work. So we have the pattern, okay, surface pattern on top of the PDMS thin films. And PDMS thin films made soft material, and the mechanical under stretching or the tensor force or compression force, okay, you can easily change, okay, the pattern, surface pattern on top, okay, like the grating structure. So, this work is succeeding, okay. You can see that, okay, as you increase the strain, the radiated heat flux, they drop dramatically. And next slide here, okay, just summarize, okay, this some of the work actually we combined the previous 2 mechanisms, okay, to achieve the dynamic control of the radiative thermal transport. So we combined, okay, the phase change material VO2, and also we combined, okay, the mechanical deformation mechanism. So we also redesigned, okay, near field enhanced thermal diode and near field enhanced thermal transistors, okay, and under mechanical deformation, or apply this one, okay, in okay, the environment with a thermal gradient, okay, you're able to increase, to change the thermal diode and the thermal transistor, okay, like performance. Okay, yeah, that's it. So thanks very much.
Thank you, Chi. Questions?
Yes.
I guess last time I missed your talk, so the first question is, now you got about 3.5 times of the thermal evaporation limit. Have you looked into explaining them? Why?
Yes, really good question. Yes, I remember this one. So the thermal evaporation limit is just 1.4, about 1.4 or so, right?
Yeah.
And also, as you also realize, the Guihua use group, the hydrogel also already almost double that. And for our work, we use the carbonized, okay, the cow manure, okay, we already achieved up to 5.3. That's almost 2.5 times. And we tried to explain the fundamentals. And as we explain in that paper, actually, but it's still not clear to us. As we explain the paper, actually, this comes, it came with the reduce, actually, the latent heat, actually, of the porous materials. This is the only way actually we can explain that. And also, we did a calculation in the paper. We calculated the efficiency, the solar energy conversion efficiency for this power structure. The efficiency is over 300%. 300%. Actually, we got actually questioned a lot actually by reviewers, and the reviewers said actually, how could actually achieve efficiency over 100%? But actually, it's not. It was not unique. a lot of group, I mean, in there, if we use their data, experimental data, and if we put into the calculation of the conversion efficiency is all over 200%, even in the Evelyn Wang's group and the 200%. So we calculate the efficiency up to 300%, and we still couldn't explain why actually this material with a high efficiency. The only term actually in the calculation of efficiency is the H value, the latent heat of this material. So that's why we thought actually maybe this because of this H value is totally reduced because of material or because of interfacial heating.
That explanation doesn't work, I tell you, because
yes,
when H is reduced, you should see the water get really cold, right?
Yeah.
When water go from outside to inside,
yes,
if your latent heat is reduced by a factor of 3,
yes,
you will create the cooling of that big. Then your water, so in that case, when the sunlight come in,
yeah,
you will not heat up the object, you will
That's
really cool down the very cold water. So we actually did a lot of this measurement.
That is true. We discussed that a few years ago.
Work.
Yes, so you're right. I mean, we also monitor, the temperature of the water, and also at the bottom of our evaporator, the water is not cooled.
Right.
So that's why I see that. So still, actually, we do not have a clear answer actually to that.
Yeah. Yes. I guess I got a 2 practical questions. Did you collect the water?
Yes, we collect water.
What's the maximum yield, the water yield you have?
What do you mean the maximum? It's the rate, right? It's the rate actually.
Yeah. What's the maximum? So you have an evaporation 5 liter or 5 liter per meter square per hour.
Yep, 5 pounds, right?
In terms of water production, how much you have?
We measure that for 1 day, for 24 hours. Okay, it's not that efficient because actually we do not have to have the direct sunlight throughout a day. Okay, we run actually the water evaporation rate for outdoor applications, from 8 a.m. till 8 a.m. in the second day, and in Boston actually we have the sun exposure actually for about 6 hours, and we can observe the really high water actually evaporation rate actually achieved during maybe the early afternoon. So we obtained for really small evaporator actually we build up, we collected about maybe 3.5 kilos in our water container.
So if you normalize it to per meter per day, how much you have water production?
Yeah, I forgot actually exact value, but in our paper actually we did have that value for the water production a day. We did have the data, so I need to go back to check.
You gotta take a 6 hour.
Yes.
5 kilo per evaporation.
No, actually we cannot simply do that.
You get 30 liter, right?
Yeah.
If you of course if you
that is true. Yes.
You collect all that.
Yes. Yeah.
Right? 30 liter is a lot, right? Because that you could look at make it
But we couldn't achieve that high.
And the maximum I've seen so far is about 15 to 18 range. I just wonder whether you got that.
That is true. We did have the data actually in the paper, for throughout the day, how much water actually production, but it's not that high.
Not one more.
Yeah.
Another question?
One more question.
Well, the last question.
On the paper, really the cooling.
Yes.
Have you checked in terms of reliability? Because you put this paper under sun. I mean, say you put a plastic under sun, you will degrade, right? So I'm just curious.
I mean, we demonstrated experimentally for systems like this. We place the paper in winter and in summertime outdoor for 30 days, and then we just brought them back, to the lab, and then we just measure their solar reflectance and the same. So 30 days outdoors in Boston in summer and winter. But the material actually is stable, is robust. Yes. And also we run actually not only for the optical property measurement, also for the contact angle. After 30 days, it still maintain actually really high contact angle up to 165 degrees.
Okay, we thank G and all the speakers of the session.